Continuing on, this is the second video for class 12, and we just talked about safety factors and uncertainty, right? And just kind of showed where safety factors and design factors and kind of talked about why they're needed. Let's talk about where some of them, or at least a portion of them, should come from. And so we needed to have a little bit of discussion in statistics. Now, I'm not much of a statistics guy. I don't think I ever actually took a class in statistics, so I'm going to try to give you more of my layman's description of the approach. And the big idea in statistics is we find a trend, a behavior in nature when something somewhat random occurs. We see some variability, right, in the results of something. Like, maybe I like to think of, like, maybe you're throwing a coin at a target, right? I'm just going to toss something at a target, and sometimes it's going to land in the center, but you do it enough times and there's going to be this distribution. The average is going to be pretty close to the center, but they're going to get a little bit spread out first and worse. So you can kind of think of it being like a pile, right? Eventually you put through enough little coins in there and it would generate a pile, right? Maybe that's not the best thing to be talking about throwing, but if you're always aiming for the center, you're not always going to hit the center, and it's going to start spreading out right there. And that informs us this natural distribution. Sometimes we call it a normal distribution or a Gaussian distribution. There are other distributions, but for many different things that are that occur, there's just sort of this like kind of natural thing that we observe that they happen, and we can work backwards to there and try to figure out what the percentage of chances of an additional one of being one, or if it already exists, we could pull one out of the pile at random. And what are the chances that it's going to be one this close to the center, right? So we have this little bell curve thing that's happening right there, and we've come up with a way to describe this curve and the width of it. It can vary in height and in how narrow or how peaky it kind of gets. And so we use parameters to try to describe that. And instead of bothering with this crazy equation right here, we create like a table, like a sort of like I don't want to use the word normalized, but it is kind of normalized. We kind of like remove the specificness of it, so we have a generic curve, and we use the table as the means of using this generic curve. And the parameters that we use we take the average or the mean, which we use as mu, and we have something called a standard deviation, right? It's like, what is a standard deviation? Well, it's more complicated than maybe we wanted to come up with, and I don't remember off the top of my head what the definition was, but we could look it up, right? But most of the time, I'm just going to put it in Excel and get a standard deviation. There's two different types, by the way. So I'm going to take a look. There's the S type and P type, I think, and just they're not that far off from each other, but statisticians really worry about them. But anyway, I think it's a sample and population. I think that's what it's called. Anyway, we could look that up. So we have the average and the standard deviation is our primary parameters that we're going to use, right? And unfortunately, standard deviation uses sigma, where we're going to use stress sometimes as sigma. So just remember, it's got this funny little hat on top of it. That's sigma, right? And we have probability of failure. We could have that. And so if we subtract that probability of failure, that's going to be like a decimal place. We can think of it as a percentage, but decimal place. If we want the reliability of something, what we need to do is subtract it from 1. And that will be how reliable. So like if we say the probability of failure is 10%, or we could say that we did a bunch of test runs and 10% of them failed. That's the probability of failure. The reliability is 90%. That makes sense. And we also know that if we have a reliability of a system, this is kind of important later on, what we do is we need to multiply all of them by each other. That's what that big capital pi is. So like if something is if we have two bearings on a piece and one is 90% reliable, the other is 90% reliable, the total reliability is 81% of the machine, right? That is the chances that one or the other is going to fail. That's not additive. That would have been like 80%, but it's multiplied. So at 0.9 times 0.9, right? And the means at which, so we wanted to try to use tables. So here's an excerpt from table A10 in the back of the book for this normal Gaussian distribution. And what do we use is this parameter z. And what is z? That's really a standard deviation. We like normalize standard deviation. Our first thing is for whatever number we're using, x, we subtract out, right? So we subtract out the average of the thing, and then we divide by a standard deviation. So now we have like this normalized thing, and we can go back up into this and find the z, and it's organized by, here's the first by tenths, and then we have by hundredths right here, right? And we can just find our z, and we can pick this out, and that's going to be p, right? That's going to be this pf, especially if it's a negative value, right? If it's not a negative value, right? So we might have to subtract this from 1, and then it would be the probability, right? So that's really so that we only have to do 1/2 of this thing. We only want to do 1/2 of this curve with the table, so because it's symmetric, right? So we go ahead and use. I think I described that correctly. But just looking at this thing right here, where you see, and by the way, they're using alpha here instead of PF. But I think we should use. I think that's correct. Yes, I believe so. So anyway, it's a lot easier to see it done than it is to explain it, right? So if you're new to statistics, well, let's just take a look at examples and try to absorb it and go back and keep looking at what this is, and you'll start to appreciate what you're really doing when you see it getting used. If you've taken probability and statistics, you're probably making fun of me of how much I've just butchered the whole thing, but that's okay. I don't mind looking like a fool. I like this from a different book. Here is the sigmas, and if you've ever heard of Six Sigma, that's a managerial quality philosophy kind of thing to try to reduce deviations, right? They're saying that 6 sigmas, if you can stay within 6 sigmas, you get like 0.135% chance of failure, right? So that's going to be like an acceptable amount of like reliability in something. I think that's why they call it 6 sigma, but Wikipedia, you'll see. Maybe I got that wrong. And by the way, this is an interesting like little graph right there. You can see sort of like the log. This looks relatively loggy, but I don't think it is. But anyway, you could look up the number of standard deviations z, and you could see this thing plotted out. Here's an excerpt from Shigley and Mish's Standard Handbook of Machine Design, and you can see this as it applies to strength. All right, so here's material of variation, and that looks pretty good in this one, but they're also showing some other ones, right? With the number of tests and the yield strength. You could see, and this is between 40 and 60, right? So this thing probably has a strength at just below 50 is what gets published for the yield strength. But there's some variability, and you also notice that it doesn't actually form a Gaussian distribution. So that's another thing that might want to be aware of. The Gaussian distribution is not the only distribution that exists. There are other distributions. One that we used later in the book is Weibull, and that kind of has sort of a skew. It kind of leans to one side. But it depends. But a normal distribution happens quite often, and it's the one we use the most often. So that's the one we're going to discuss. But just be aware of some of these other ones that are possible. Right, other distributions that are possible. But you can see here's the number of tests that get done and what the tensile strength was of in these tests right here. So, all right, and then another books one. I don't know why I have so many in there. So I'm going to go to the example first. So I'm going to go to a simple statistics example first, and it's this one right there. And then I'm going to make another video. Yeah, I think I'll go after this, right? So here's the simplest example of a, simplest example. So example 1.4 out of Shigley. A shipment of 250 connecting rods. The mean tensile strength is found to be 45 ksi, and which has a standard deviation of 5 ksi. Right. So that's the strength. The average strength is 45, but it's like the standard deviation is 5, and that kind of tells us how like spread out the thing is. Right. Is it narrow and peaky? So I like to draw that out right there, right? So we have an average right there, and it gives us sort of it gives us a value of the thing, and it could be it could be distributed this way, or it could be really peaky onto the thing. So that standard deviation kind of tells us how fat, right? So that's kind of telling us how far this is versus that, right? So it's how peaky and how far the two things are away from each other. Okay, so I'll stick with the camera here. So we're assuming a normal distribution. How many rods can be expected to have a strength less than 39.5? And how many can be expected to be between 39.5 and 59.5? So let me get my notes out right here. Right. So the first thing we want to do maybe is write down what our parameters are. And so we found our average of this one here, and I'm going to call it strength. S, capital S is strength right here, is going to be 45 ksi. And our our sigma, this is mu, right? Sigma right here, and we'll go S right there is 5 ksi. And remember, this is not stress. That is just the symbol they decided to use for standard deviation. It's messed up, I know. But anyway, we want to get a z parameter. We start out with a z parameter, and we're going to subtract out the average and divide by the standard deviation. So that kind of like makes it so now we're not talking specifics. We're going to talk about like this table that just kind of helps us, guides us through what that where that thing kind of fits within that over the hat, the bell. There you go, the bell. Right. So they asked for this first one, 39.5. So we subtract out 45. So it's obvious going to be, in terms of this thing right here. Here's the average right there. Right. So it's obviously over onto this side right there. And that's going to make it a negative number, right? Just be aware of that. So we're going to take 5, and what we end up finding is we get negative 1.1000. Now we look it up. We look this up. Look up in table A10. I don't know why I said it. Okay, so we look up in A10. So take the book out and look up in A10. And by the way, there are Excel functions that make this very easy to do, easier than looking it up in a book, but on an exam, whatever we might have to do. Okay, so here is the z's, and we got a negative 1.1, right? So here, right there, is, now 1.1 is in there. If it was 1.11, we'd use this. 1.12, we'd use that. You get the idea. 1.11, we get 0.1357. And we use this symbol right there. I can't remember what that Greek one is off the top of my head. I want to say it's iota. Is that even a Greek letter? I don't know. I was not in a fraternity. I was in a fake fraternity. But we looked this up, 0.1357. And what that really means is that 13.57% chance. So 13.57% chance that we're going to be less than, right? It's that's going to be over here, right? That the next sample or the things that we pick out of the sample size. So when we go to say the number, I just went down as rods, right? The rods that are less than 39.5 are going to be equal, if you have 250 of them, right? Then it's going to be 13.57% of them we could expect to be, and that's going to be 33.9, but that doesn't make any sense. So you're going to say, we're going to predict that the number of rods that are less than this right here is going to be approximately 34 rods. That's the idea. That's the big idea. And let's say that we want to say, okay, so the next one is how many are expected to have a strength between this and this. So now we saw what happens when there's a negative number right there. It's really kind of be on the left of this. If it's a positive number, it's going to be on the right-hand side of the thing. So, and it's good. And let's say that this was in the middle here. Here was our 45, right? Because there was the average, and this was our 39.5. So over here it's going to be slightly more. Here's our 59.5. I guess yeah, kind of like that. Yeah, sure. So we want to these are going to be this right here would be the probability that it's going to be greater. We actually want to have the probability it's going to be less than, and we want to find this zone right here. That's our goal. So in part B. So what we want to do here, and maybe this should have been the 39.5 Z. Let's take a Z for 59.5. So we're going to take, once again, our 59.5, subtract out the average, divide it by the standard deviation, and what we end up getting is 2.900, which makes it like really easy. Somebody did this number on purpose, right? So we come back into here, boom. And did I do this wrong? No, there it is. Here's our Z, 0.00187. So, well, not our Z, but okay, 0.00187, right? But we're told, like, if we are, if we had something that was positive, what we should really use is 1 minus 0.00187, right? This is the chances that the thing is going to be greater than 59.5. Not a whole lot. That's less than 1%. But here we're going to get 0.9981. That's going to be the chances that it's less than 59.1. So if we want to have like the probability, I guess I used P. I think it's correct. Subtract this and that. So we have 0.9981, subtract out 0.1357, and what we're left with is 0.8624. And now we want to have, say, the chances, the rods that are, let's see, greater than 39.5 and less than 59.5 is going to be equal to 0.8624 times the population 250, and that ends up equaling 215.6. I don't know, you could round up or round down. I would say, I think I would round down, but I think maybe the book round up, right? It's hard to say approximately 216 rods, right? But you don't want to have like a fraction of a rod, because you could actually measure this, right? You're predicting. So I'm kind of like, my mindset is to be maybe a little more cautious, but not to be too cautious. All right, so we're going to use this was the introduction to probability, and the idea of reliability. So we're going to now extend it in the next example. So let me see here. All right, so here in the book, they decided to go with 216 rods. All right, now you could read this yourself, but hopefully maybe by working through it in a video, it might make it a little bit more clear what is going on and make it less, I don't know, intimidating maybe. 20 minutes worth of stuff.